Welcome back to our video lessons. We're going to extend our study of parallel and perpendicular lines onto the coordinate plane, and the rest of this unit will be an introduction to coordinate geometry. Before we get too involved with parallel and perpendicular lines on a coordinate plane, we need to be familiar with a few formulas that will be useful to us along the way. The first one is the midpoint formula. We know that a midpoint of a line segment is a point that divides the segment into two congruent segments. Up until now, we've really just been considering a midpoint like a one-dimensional midpoint. So we're looking at a segment that's horizontal, lying along a number line, or maybe a vertical segment lying along a vertical number line. But here we see a segment in two dimensions. It has x and y coordinates for its endpoints. And by deduction, by logical reasoning, we can probably conclude that the midpoint of this segment is 1, 1/2, or 1, 0.5. The x value of the midpoint being 1, because as we can kind of visualize, that 1 is halfway in between the x coordinates of the endpoints. So that 1 is 3 units from both of the endpoints. And likewise, the 0.5 or the 1/2 is 1.5 units from the y values of the endpoints. So we have a formula to calculate the midpoint of a segment on a coordinate plane. And that formula looks big and scary. Okay, but I encourage you to really just think of this formula as the average of the x coordinates and the average of the y coordinates. As you can see, we're taking the sum of the x coordinates, dividing it by 2. That's just taking an average, and likewise the sum of the y coordinates and dividing it by 2. So if you just think of this as an average x and average y, you don't have to get bogged down with memorizing a formula. Let's take a look at some examples of the midpoint formula.
Okay, so our first example is using the midpoint formula to find the coordinates of the midpoint of segment PQ with endpoints P, -8, 3, and Q, -2, 7. Okay, so recall the midpoint formula is the average of our x coordinates and the average of our y coordinates. And I'm going to reiterate that it's important to just remember that it is just an average. Okay, an average of the coordinates, rather than trying to memorize the formula, because it could get confusing with all the 1s and 2s and everything in it. So if we take the average x's, -8 plus -2 divided by 2, okay, we get -10 divided by 2, which is -5. That's our x coordinate. The average y coordinate is 3 plus 7 divided by 2, which is 10 over 2, which is 5. So our midpoint is -5, 5. Another example that involves a little more algebra, coordinates of the midpoint of VW with endpoints -2, -6, and x plus 2, y plus 3. So again, no different. We're going to take the average x value, -2 plus x plus 2 is our second x value, divided by 2. Okay, well notice this -2 and this 2 are just going to zero out, going to cancel out. So our average x value is going to be x over 2, or half x. Our average y value is -6 plus y plus 3, divided by 2. And simplifying, we get -3 plus y over 2. And that's our midpoint. So sometimes, our midpoint is just going to be expressed in terms of x and y. One last example with the midpoint formula. Slightly different here. We have M is the midpoint of AB, and we're given the coordinates of A and M. So if we could visualize what this looks like, right? If we have A B, and the midpoint M, we're given A and we're given M, and we're being asked to find B. Okay, and we've done this before on just thinking of it in terms of one dimension, in terms of X or in terms of Y, but we've never done this in 2 dimensions on a coordinate plane. Okay, and here's a case where you have a couple of different options. Okay, one option would be to use the midpoint formula. Again, I'm going to write that up here just to remind us. The average X value and the average Y value. Okay, so in this case, we don't know what x2 is, right? We'll call B x2, y2. We'll call A x1, y1. So we don't know what x2 is. So we're going to substitute everything into the midpoint formula. -4 plus whatever our x value is, divided by 2. Okay, and we know what it equals, right? We know that that equals, I don't need this parenthesis here, we know that that equals 1 because the coordinates of our midpoint, are 1, -10. So the x value of our midpoint is 1. So if we find the average x value, we should get 1. And now we're going to solve this. This is a proportion. Think of this like a proportion, 1 over 1, and we can cross multiply. Right, so -4 plus x squared equals 2, and not x squared, sorry, x2. x2 equals 6. Okay, so the x coordinate of point B is 6. We'll do the same for the y coordinate. y1 is -3, plus we don't know what y2 is. That average is going to be -10. Cross multiply. -3 plus y2 equals -20. So y2 equals -17. Okay, so that's one way we can solve this problem, by using the midpoint formula. We do have another method that we can use with the midpoint formula. I'm just going to create a new page here. Okay, so let's just look at another view of this problem. Remember that we had the point A, -4, -3, and we had the point M at 1, -10. And we don't know what B is. Okay, well, we figured out what B is, but this is a different way, a different view of the problem, and also a way to check our work. Okay, since we know that the midpoint is halfway between A and B, that means we know that this x value is halfway between -4 and what other x value we have. Okay, so another way to look at this would be to say, well, from -4 to 1, we have increased 5 units. So that means from 1 to whatever my B value is, the x value of point B is, we have to increase another 5 units. Okay, so 1 plus 5 is 6, the same 6 that we got before. Likewise, on the y side, from -3 to 10, we've decreased 7 units. And since M is the midpoint, to get to B, we're going to decrease another 7 units to -17. So here we go, the same midpoint, the same endpoint that we got using the formula, we can get just using a different understanding, an understanding of what the midpoint is.
The next formula we're going to be using throughout the rest of the year, really, and we'll study this in more depth later, is the Pythagorean Theorem. This should be familiar to you from 7th grade, possibly. The Pythagorean Theorem says that in a right triangle, the sum of the squares of the lengths of the legs of the right triangle, the legs are the perpendicular sides of the right triangle, is equal to the square of the hypotenuse. So if we take a look at this diagram, a squared plus b squared equals c squared. And like I said, much later in this course, we'll go into more depth on the Pythagorean theorem, and we'll understand why it is the way it is, and we'll look at some proofs of the Pythagorean theorem later on. But for now, we'll just be utilizing this formula to solve some problems. So here are some examples of the Pythagorean theorem.
Okay, let's take a look at using the Pythagorean theorem on the coordinate plane. You're probably familiar with the Pythagorean theorem from middle school, and most likely you just did it on a triangle, right? Not necessarily on the coordinate plane. So let's look at the Pythagorean theorem on the coordinate plane, remembering that we said the Pythagorean theorem says that the sum of the squares of the sides of a right triangle is equal to the square of the hypotenuse. Okay, so what does that mean? We need to draw a right triangle here on our plane. Okay, so we'll draw one leg and the other leg. There's our right triangle. And we can see that this leg here, we just count them right up, right? 1, 2, 3, 4, 5, 6 units. And this leg here is 1, 2, 3, 4, 5, 6, 7 units. Okay, we plug it into our formula. 6 squared plus 7 squared equals c squared. That's 36 plus 49 equals c squared. So 85 equals c squared. And so we could say c is the square root of 85. That is simplest radical form, because there are no perfect square factors that go into 85. Or we can also say that c is approximately equal to 9.22 if we want to round to the nearest.
And finally, we have the distance formula. And this distance formula looks even bigger and scarier than the midpoint formula. All those x1s and x2s, and now we've got a square root and some squareds and everything. But I'm here to tell you that the distance formula is really just the Pythagorean theorem in disguise. And we're going to take a look at some examples of the use of the distance formula so that you can see why I say that it really is just the Pythagorean theorem in disguise. So again, I'm going to encourage you to not get bogged down with memorizing the distance formula, but instead understand how it relates to the Pythagorean theorem, and then you won't really have to really memorize anything. So we'll take a look at some of these examples of the distance formula, and we will look at these in more depth in class tomorrow.
Now, as we said, the distance formula is really just the Pythagorean theorem in disguise. Okay, so we want to find, we want to answer the question, is FG congruent to JK? So just for demonstration purposes, we'll use the Pythagorean theorem to find the length of one of these segments, and we'll use the distance formula to find the length of the other segment. So let's use the Pythagorean theorem for FG. So we draw our right triangle. You see we have a leg of 3 units and a leg of 4 units. 3 squared plus 4 squared equals c squared. That's 9 plus 16 is c squared. So c squared is 25, which makes c 5, technically 5 or negative 5, but we don't care about the negative 5 here because we're talking about lengths. Okay, and now let's use the distance formula for JK. All right, so the distance formula says the square root, d is the square root of x1 minus x2 squared plus y1 minus y2 squared. Now, why do I say that this is the Pythagorean theorem in disguise? Now, take a look. If we were to square d, this square root disappears, right? Because if we square a square root, it goes away. So we end up with x1 minus x2 squared plus y1 minus y2 squared. We'll take a look at the distance formula and the Pythagorean theorem, which I didn't write, a squared plus b squared equals c squared. Now take a look. That d squared is really the hypotenuse of your triangle, right? If you think of this JK, we're finding the distance. That's really just the hypotenuse of the triangle that we could draw. The a squared and the b squared come from finding the y distance and the x distance, right? So the distance from one x value to the other x value is, we subtract to find that distance. And to find the distance from one y value to the other y value, we subtract to find that distance. Okay, so that x distance is the same as one of the legs of your right triangle. That y distance is the same as one of the legs of your right triangle, as the other leg of your right triangle. So the distance formula and the Pythagorean theorem are really the same thing. Okay, but we'll use the true distance formula with the square roots and everything to calculate the distance from j to k. Okay, and it doesn't matter because we're squaring it. It doesn't matter whether we choose j as x1, y1 or k as x1, y1. So I'm just going to start with j because it's on the left. The first x-coordinate, the x-coordinate of j, is -4. So -4 minus, this is -1, -3, minus -1, be careful with those minuses and those negatives, squared, plus 0 minus -3 squared. So distance equals the square root of, this is -3 squared plus 3 squared, which is the square root of 18, which if we simplifies the square root of 9 and the square root of 3, which is 3 square root of 3. So we have 3 square root of 3 as the length of JK, and we have 5 as the length of FG. So these are not congruent.
Okay, we'll see you in class tomorrow.